Hello. This is our first video for Math 111. So there's a lot of challenging algebra topics in Math 111, and this video and the first homework assignment will just be kind of reviewing old algebra topics. And I find often that the review topics supposedly are actually things that students have never seen before. Kind of depends on which math classes you took in high school and things like that, and if you had taken a math class prior to this in college or not. So this is going to be a mixed bag. Some of you, everything will be review and it'll look simple and easy, but for others, maybe it'll be all brand new. But I tried to pull together a lot of the algebra topics that we will need as prerequisite knowledge for the topics we'll cover in this class. So the first week and maybe part of the second week will be a lot of review stuff. And feel free to always come back to this video if you come to a new topic later in the semester and you think, hey, I don't remember the prerequisite stuff. Maybe I think I kind of remember that we went over it in the first video. You can always feel free to come back and watch this again. Just fast forward to what you need, and yeah, and even now, if there's things you know, feel free to fast forward. Go skip anything you already know. So the class technically starts in chapter 1, but this is called chapter P, the prerequisite stuff. And yeah, like I said, I think it's important because a lot of students I find don't know all of this stuff, which is typical. I think it's normal. Yeah, if you know all this stuff already, you must have gone to a very fancy school or something. I don't know. Let's see. So just the very basics. Let's talk about algebraic expressions here. Let's see if, as obviously you know at least, that sometimes letters are used to indicate a number that is unknown. I can't write the number because I don't know what it is. So we just call it, X or some other letter. Kind of like when you don't know someone's name, you say, that guy, let's call him Bob. I don't know. Bob did this and he did that. Yeah, you just give it a name, even if that's not the right name. At least you could refer to this thing as something. So let's see. If a letter is used to represent various numbers, it is called a variable. So that's what we'll call any letter you see in math. And as you probably guessed, the higher you go in math, the more variables there are and the fewer actual numbers there are. A combination of variables and numbers using the operations of addition, subtraction, multiplication, or division, as well as powers or exponents or roots like square roots, which we'll talk about later in this video, is called an algebraic expression. Evaluating an algebraic expression means to find the value of the expression for a given value of the variable. So they'll give you just this group of numbers and maybe variable or variables that are adding or subtracting with each other, multiplying or dividing, and they might have exponents or powers, they might have roots. But if you're given a value of X or the variable, you're to replace it with that value and then simplify. So, and then if you have just something to a power or an exponent, they call that an exponential expression. So just the basics, because we'll be using this terminology as we go. And then, yeah, I don't want anyone to get kind of confused about the terminology, because that's the main thing. And then we have to learn how to do these operations and simplifying and everything. So this is important. The order of operations, you perform operations within the innermost parentheses. This is when you have an expression, a big, just like I mentioned, kind of there's a bunch of numbers. Maybe they're adding, subtracting, multiplying, dividing. There might be powers. There might be parentheses, which we haven't mentioned yet in this video. And there might be roots. But there's a certain order you're supposed to use or do the operations in, or else you'll get it wrong. So you're supposed to first look for parentheses. If there are no parentheses, you can skip to the next step. But if there are parentheses, you should simplify that. If it involves a fraction, you treat the numerator and the denominator as if they were each enclosed in parentheses. So if you had, I don't know, I'm just making this up, 6 plus 3 times 5 over 7 to the second power plus 8 minus 4. I don't know, I'm making that up, but it says, as it said in that paragraph above, kind of simplify the numerator and denominator separately as if they were each enclosed in parentheses. You simplify this down to just one number, simplify the denominator down to just one number, and then once it's a number over a number all simplified, then maybe you could do something with that. You can go further maybe. Yeah. Okay, let's see. What else? So once you've simplified parentheses and or if there is a fraction, you would simplify the numerator and denominator separately. If those are kind of taken care of, or maybe they don't even apply to your current problem you're doing, then you would evaluate all exponential expressions. So kind of scan everything in the expression and see if there's any exponents. If there are any exponents, try to evaluate that. So if you saw 5 to the second power, replace it with 25, something like that, just evaluate what it is. And then you can move on to the next step, let's see, which is perform any multiplication and division as they occur, working from left to right. So I'm a lot older than most of you, so but when I was a student, I remember them saying multiply and then divide, no matter what order you see them in. So if you saw something like 36 divided by 3 multiplied by 4, I remember my instructor, they said, do the multiplication first, no matter what, and then do the division. But that actually gives you the wrong answer. You should just go left to right, dividing and multiplying. So as I just scan this from left to right, okay, the first operation I see is division before multiplication. So I should do the division first. 36 divided by 3 is 12, and then multiply by the 4. And often you'll get different answers depending on the order you do it in. So you have to do it, like I said, multiplication and division is on the same level of importance. You just go from left to right. Kind of like you're reading. As you read a book, the words on the left go before the words on the right. So same with operations in math, as far as multiplication and division go. And then once all the multiplication and division is all done and simplified, then the last step would be, at this point, you might have just one number, so you're done. But if you have more operations, all that should be left is maybe adding or subtracting, or both. If there's more than that, maybe you didn't simplify something in steps 1 through 3 up here. Yeah, so, and then same thing with adding and subtracting, just add or subtract from left to right. So maybe we'll try to simplify this expression here. And here's the expression. And I think we mentioned this a little bit already, but this is an expression, what I've boxed there, not an equation. Equations have equal signs. That's how I know that what I boxed there is not an equation. Signs, because there is no equal sign there. But if it was that expression equals something, then it would be all of a sudden an equation. So anyway, they're wanting us to evaluate it. They're saying, what would this expression be equal to if x was 13? So I'm just going to go ahead and rewrite that expression that's boxed, but replace x with 13. So where that x was, I'm putting 13, but everything else is staying the same. Notice the 8 stays the same, the plus sign, the 6, just the x is changing, the subtraction sign's the same, the 3, and then the power of 2 on the outside. Now I need to do order of operations. So we said, on the previous page, it kind of talked about it, but this is the easy way to remember it, PEMDAS. P stands for parentheses, and then E stands for exponent. M/D is multiply, divide. They put them on the same level because, like we said, it doesn't really matter which order. It's just go from left to right and do multiplying and dividing. Okay, blah, blah, blah. Okay, and then add and subtract. Subtract. So I want to do the first. This is number 1 here, parentheses. I scan my expression. I do see there is parentheses, so I'm going to prioritize that. Everything else I'm going to keep the same. 8 plus 6. I'm very tempted to add that right now because it's in the very front. If I was reading a book, I would be doing that first. I would read the left words first. The math's a little different. I want to subtract, I guess, the 13 and the 3. That's why it's in parentheses. If you see something in parentheses, that means that's the priority. Do that first, and then whatever else is going on. So I'll do that subtraction first. 13 subtract 3 is 10. Okay, and then I can't forget that little 2. He's going to matter later. Now, I mean, I do see parentheses. I left them there. They're not really there for any reason. I guess the reason I left them there is because I'm worried if I take them away, I'll see the 6 in the front, like 8 plus 6. And then 10, if I just write it like that, that all of a sudden looks like 610. So I guess I leave the parentheses there just to separate the 10 from the 6, so I know they're not part of the same number. But anyway, it's just kind of technicalities. Okay, we've done parentheses now. Part 2, or the second step, would be exponents. There is some exponent there. I really want to add these numbers, but I can't do it yet. It's very tempting. It's like a cookie that's just sitting there on the plate. I'm not supposed to eat it yet, but it just looks so good. At 8 plus 6, anyway. So it's not that big a deal, right? 10 to the second power, that's 10 times 10. 10 to the second power. Yeah, if you ever see an exponent, that means multiply this big guy down here by himself this many times. So 10 to the power of 2 means 10 times 10. If it were 10 to the third power, it'd be 10 times 10 times 10. Anyway, on and on and on. So 10 to the second power is 100, 10 times multiplied by 10. Okay, and I think that's all the exponents. And again, I'm just leaving parentheses there, just so I'm not thinking 6 next to 100 looks like 6,100. That's not what it's supposed to be. So that parentheses are there, but they're not really serving a purpose. They're not like, I don't need to prioritize any operations that are inside it. So I'm moving on to the next step, multiply or divide. If I look from left to right here, boom, 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 there's a plus, that doesn't count. I'm looking for multiplying or dividing. Here actually is multiplying, even though you don't see a multiplication symbol or anything really indicating multiplication, it's still there. 6 multiplied by 100 is 600. And now, I don't know if you really need to consult the order of operations. At this point, just there's not much left to do. I mean, add and subtract from left to right. Although if there were still any multiplying or dividing to be done, I would do that next. You know, I went from left to right, I multiplied. The first thing I saw that was either multiplication or division. If at this point there was still any multiplication or division left, I would do that, exhaust all the multiplication and division before I get to that last step of adding and subtracting. But there's only one thing left to do now, it's add. 8 plus 600 is 608. So there's your answer. And if you mixed up the order of operations, if I had done what I wanted to do is add the 8 and the 6 first, then I would have gotten this whole thing wrong. And then, yeah. And so there's a lot of places I could have done something wrong and then gotten the whole problem wrong. Yeah, so, but as long as you're careful and you follow the order of operations and maybe don't skip steps if you can help it, because skipping steps or doing a lot of stuff in your head. Anyway, for me, I end up making mistakes. Maybe a lot of people, that's not true for them, but for me, yeah. Okay. I'm gonna go. Okay. All right, now we'll talk about a set. So this is something it's not too complicated, but it might throw someone off if we are doing a certain section in Math 111 and we come across a set and it's just assumed that everybody knows what it is. It might throw you off, or it would throw me off as a student. So I just want to introduce it so later it'll seem familiar and it won't throw you off. So a set is just a collection of objects whose contents can be clearly determined. So it wouldn't be unknowns usually. It's going to be usually a set of numbers, I guess. In just a purely logic class, you might see things other than numbers, but in this class, we're just interested in numbers. The objects in a set are called the elements of the set, and we use braces, these I call them squiggly brackets, but I guess they're called braces, to indicate that we are representing a set. So if you see this and just a bunch of numbers in there, I'll put 1, and then I'm just making this up, okay, 6, maybe a negative number just for fun, 0. I mean, put a fraction if I want to, 3/4. That's a set just full of 5 numbers. 1, 2, 3, 4, 5. So and that could be a solution to an equation, or anyway, that's how we'll write our answer a lot of times in future sections of this class. This is if you want to represent a finite number of elements, as they call them. The elements in this set are 1, 6, -3, 0, 3/4. Yeah, and we'll see later in this class if you want to represent not a finite number. Finite is the opposite of infinite. What if you want to represent an infinite number of elements? Then that'll be something else. But that's if you ever have a finite, not infinite number of things you want to represent, that's what we'll use as these braces or set notation. Yeah, let's see. Okay. Now, what else? We've got, so, and another way to represent an infinite set or an infinite number of things is see how in this set they have the numbers 1, 2, 3, 4, 5, but they don't end it there. They have this dot, dot, dot. That's called roster, the roster method of representing a set. The 3 dots represent that this goes on forever. There's no last element. This is going to be 1, 2, 3, 4, 5, all the counting numbers. If you kept counting forever, 1, 2, 3, 4, 5, 6, 7, then all those numbers are going to be in here. This is actually an infinite set. But for the most part, you might see that in a future math class, especially if you have to take a lot of math. But in this class, usually if there's an infinite set, we'll use a different kind of method to represent it, and we'll see that in the future, in future sections. So, okay, yeah, let's see, what else? If a set has no elements, it's called the empty set. We don't see that too much, but especially if you have to take a lot of math classes, this is kind of nice to know. It would either just look like this symbol, it's like a circle with a line through it. That means it's empty, there's nothing there. Or you might just see the squiggly brackets or the braces with nothing in them. That would be like if somehow you were to solve an equation and you try to solve it, but there actually are no solutions in disguise. It was a kind of a false equation that has no solutions. Then maybe you could represent the number of solutions as the empty set because there are no solutions. I guess is where you might see it someday. The number line, I don't think we'll use this too much, but just the rare occasion where we do, it'd be nice to have seen it before. A real number line is a graph used to represent the set of real numbers. Now we're not talking about necessarily the x-y coordinate system, where the y-axis is vertical, the x-axis is horizontal. This is just one kind of axis, I guess, where 0 is right in the middle, all the positive numbers are to the right, and all the negative numbers are to the left. But if you are familiar with the x-y axis stuff, then think of this as just the x-axis all by itself. Whereas if you were graphing, if you've seen graphing lines before on the x-y coordinate system, that's maybe a little more complicated. That's if you have two variables running around. This is what if you only have one variable and you want to represent the value of that variable somewhere on a graph. Yeah, so this is probably even more simple than you're used to from previous math classes. But once in a while, yeah, we only have one variable. So this is how we could kind of represent it. Let's see. And of course, like in the XY coordinate system, the origin is the middle, right? Where 0 is. What else? And then the numbers that are to the right of 0 are positive. The numbers that are to the left of 0 or the origin are negative. So probably a lot of things you've already seen, but just in case, I think there's one section, maybe two sections of this book where we have to actually talk about the number line. It won't be very often, but just for the times we do, it's good to have seen it maybe. Especially for what this is talking about now. Inequality symbols, that's probably when we'll use the number line. So it kind of makes sense that this is right afterwards. Inequality symbols always point to the lesser of the two real numbers. I always remember that. So if it looks like this, which way is it? It looks like an arrow, or at least part of an arrow. It's pointing at the smaller number. So you'd see a smaller number on the right side and a larger number on the left. That's saying 2 is greater than 1. But if you saw, if it was backwards, the other way, that means less than. So I would put the smaller number on the left. And it doesn't have to be 1 and 2. I'm just really boring, and I don't think of a lot of fun examples. I got the most boring ones. 1 is, we'd say, less than 2. So I think we'll do inequalities like these so often that you'll probably memorize it. But if you see it facing this way, where it's open on the left and pointing on the right, that's greater than. And then if it's the opposite, where it's pointing to the left and then open on the right, it's less than. I always remember that someone told me, if you have a less than or a greater than, whatever, just make it look like Pac-Man or some, I don't know, or an alligator or something. And it's always wanting to eat the bigger number. So if this is Pac-Man right here, whatever, alligator, I can't draw an alligator, so just, pretend. He's going to be trying to eat the bigger number because he's really hungry. And same thing with this guy. He wants to eat the bigger number because he's really hungry. So if you ever have a hard time remembering which way is which, is this the greater than? Is this the less than? Just remember, he's always wanting to eat the bigger number. Yeah, okay. Sounds good. That's silly. Somehow when I think of a weird, like Pac-Man, or an alligator, just how weird that is helps me remember things. I don't know why. The weirder the analogy or whatever is, the more likely I'll remember it. So this is more general. I use the numbers 1 and 2, but it could be any numbers, right? A less than B means that A is less than B. So whatever's on the left, whatever's on the right, doesn't really matter. We just call them A and B because it could be anything. But yeah, that one means less than. Let's see. And then this one we haven't talked about yet, just in this video. But this, what if I were to make it look a little different? I just had this little line beneath. It's not just a less than symbol. There's also this little guy here. That means that the number that's on the left is either less than or equal to. So it gives you more wiggle room. You could say, well, I'm not sure these numbers could be equal, or the one on the left could be smaller, I guess. It's one or the other. It's more broad, I guess, is the way I would think of it. And then A, we said that's a greater than. Greater than B means that A is greater than B, yeah. Because yeah, like we said, the little alligator or the little Pac-Man, he's trying to eat the bigger number. The one on the left must be bigger, A greater than B. And then if you added a line beneath it, again, it means it's either greater than or equal to B. So if it was 5 greater than or equal to 5, that's true. Because the number on the left could either be greater than the number on the right or equal to. And that is true, that they are equal. So that's enough. We then, when we compare the size of real numbers, we say that we are ordering the real numbers. Yeah, I guess because real numbers, like on the number line, you can always put them in order. Okay, let's see. I'm gonna get rid of all this stuff. Okay, the commutative property. So this is kind of getting into the weeds, but it's kind of nice. You know, I feel like math is kind of like playing a really complicated board game. If you just jump in and play a board game for the first time without reading the directions or knowing the rules, you won't probably do a great job and you won't have fun, that's for sure. But you kind of have to know the rules to play the game, which is kind of a weird analogy, but I think that's what these are. These are the rules of math. You can't just do whatever you want. You got to follow these rules. So they're just saying this one's pretty simple. I think it's almost everybody would think it's obvious. If someone says, here, add these two numbers, if you wanted to, you could switch their order, 5 plus 3, I have a young kid at home and they're learning this kind of stuff in school. You can either start with 5 and add 3 more, 5, 6, 7, 8. Or you could have started with the smaller number 3 and add 5, 3, 4, 5, 6, 7, 8. Either way, you're going to get to the same answer. It just doesn't really matter the order the numbers are in, if that makes sense. Yeah, and I think that's probably pretty obvious. That everybody in this class could have come up with that rule on their own. It's almost like, do we really need to write that down? That's so obvious. And then there's the same thing with multiplication. They call it the commutative property of addition. This one's the commutative. Commutative means it doesn't matter what order things are in. You could switch them. Same thing with multiplication. If I were to multiply, 5 multiplied by 3 is the same as 3 multiplied by 5, or any pair of numbers. It doesn't really matter their order. Yeah, but notice that's not true of subtraction or division either. It's only true of addition or multiplication. Because if I did subtraction, 5 subtract 3, that is not equal to 3 subtract 5. Because in one case, you're going to get a positive. In one case, you're going to get a negative. So these are kind of special for addition and multiplication. Yeah, subtraction, not so much. No. And then division, same thing. Division, no. Because even, I know, I'm really boring. I'm using the same examples. 5/3, that's bigger than 1. Is whenever the numerator is larger than the denominator, that's going to be a number larger than 1. That's not the same as if I switch their order. 5 divided by 3 is not the same as 3 divided by 5. So these commutative properties of addition and multiplication are exclusive to just those operations, not multiplication, or sorry, not division or subtraction. So then, and then there's something called the associative property. This is if you're adding not just two numbers. In the very top property, we had two numbers and we said it doesn't matter what order they're in when we add. This is saying if we have 3 numbers, A plus B plus C, whatever they are, it doesn't really matter what order they're in. If you had 3 numbers and you're adding them, you could add the ones on the left first and then add the result with the one on the right, or you could add the ones on the right first and then, yeah, like if you had 5 plus 3 plus 2, the parentheses are saying I'm prioritizing the left numbers, 5 and 3, add those together and then add 2, but it doesn't really matter. I could have added the 3 plus the 2 first and then added the 5. Yeah, when you add 3 numbers, it doesn't matter what order you're adding them in. Yeah, it probably seems like another one that's like, yeah, I don't know why we need to write these down. These are very obvious. And then there's something very similar with multiplication. If you're multiplying 3 numbers, you could do it in any order. Just pick 2 of them, multiply, take the result, multiply by the 3rd one. Doesn't matter which order you do it in. Just kind of choose whichever one seems like it's the easiest route, I guess. Whatever's easiest for you. But again, yeah, these are exclusive to addition and multiplication. Don't try to do any of these with subtraction and division because they won't. I don't know. Those are kind of like the naughty kids. They're not the good kids. The good kids are addition and multiplication. They do what they're told. They follow rules and they do nice things and everything turns out nice. But not so much with division and subtraction. And this one we use a lot, the distributive property. If you have, say there's something, this is kind of like combining the properties. There's multiplication going on because there's a number outside the parentheses with no obvious operation. So that means multiply, but then there's addition going on inside. If you want to, you can kind of distribute. Usually I think people see these arrows. Multiply A times B and then multiply A times C. So go A times B plus A times C, like that. Something like that. So that we'll use that a lot. It's maybe right now it's kind of like, why would we? It's probably hard to imagine. When would we use that? Unless you've done it before in other math classes. And then there's the identity property of addition. This one really, I think if you're sitting here and like, really, do we have to say this? Any number plus 0 is the original number back. I don't know if that's really necessary to say, but it's worth saying. For example, e.g., if we had 6, if you add 0 to 6, of course it's still going to be 6. But and I could have replaced 6 with any number, and it's going to be true. It's maybe that seems kind of silly. And then I guess the only way that's useful is if you don't know what a is. Like if you left it as a variable, if someone said, okay, a, I don't know what it is, add 0 to it. At first, it's kind of daunting. You're kind of worried. Okay, well, I don't know what a is, so can I really simplify a plus 0? Doesn't matter what a is, you add 0 to it, and it's going to be the original guy, a back. And then same thing for multiplication. If you see any number, whether I know what it is or not, multiplied by 1, it's just going to be that number back. So of course, if it was an actual number like 10 times 1, of course it's still 10. And then they didn't write this, I don't think, but the other way as well. If I saw the 1 in the front multiplied by a number a, it's still a. So it doesn't matter which way they go, a times 1, 1 times a. That goes with that. What was it? The commutative property of multiplication that we saw on the previous page. Let's see. Okay, inverse property of addition. This just says if you add a number with the negative version of that number, which they call the additive inverse, you're going to get 0. So, that's kind of weird, but if you think of it as actual numbers, 2 plus negative 2, for example, that's 0. And no, 2 is not special. It could have been any number. A number plus its additive inverse or the negative version of it is going to be 0. The inverse property of multiplication, so it's kind of similar, but if you multiply any number by its multiplicative inverse, they call it. So something like 2 multiplied by 1 over 2 or 1/2, it's going to give you 1. Yeah, because you can put the original whole number over 1, and then, they kind of simplify on the diagonal anyway. And that's true of anything. 2 times 1/2 is 1. 5 multiplied by 1/5 is 1. That one maybe is a little more useful, huh? I could see that one maybe it's not super obvious until you see it, and then you say, oh yeah, I guess that's true. Yeah. Oh, let me get rid of all this stuff. Okay. Simplifying algebraic expressions. Okay, this is important. We'll see this definitely in chapter 3 in this class. To simplify an algebraic expression, we combine like terms. Like terms are terms that have exactly the same variable factors. An algebraic expression is simplified when parentheses have been removed and the like terms have been combined. So this is it's kind of like order of operations, except if your expression didn't just have numbers, maybe there are also variables in them. Because yeah, if it's all numbers, we kind of know how to do that by now because we did an example of order of operations. But what if there was a variable in there and we don't know what that variable is? Then what would you do? That's the idea. Okay, and then wait, is that it? Oh, there you go. I was gonna say, wait. Okay, I thought I had an example, but I guess I don't. I'm gonna make it up. Let's say if you had 5x, this is maybe a simple one. I think we'll see more complicated ones later. 5x minus 3 minus 7x plus 8. I don't know, something like that. Like I said, like terms are terms that have exactly the same variable factors. So I would say sometimes it's kind of nice. This one maybe not too complicated, but it's kind of nice to look at your expression and see which ones are like terms. So here I got a 5x. Are there any other terms that have just an x attached to them? Yeah, here we go. So these guys will be like terms. As you do problems, you can always skip this step, but I notice in books and stuff, they just go really slowly. I'm going to put those two next to each other, so I know I'm going to combine those. And then the 3, or sorry, I should say minus 3 or negative 3, and the 8, those are going to be like terms, so I'm going to put those guys next to each other. And also notice that the sign that's to the left of a number or a term will always follow it. So even though this 3 is moving, the subtraction or the negative sign is following him. And then this 8 had a plus, he's following him. Anyway, now I think I can combine like terms. And when you add or subtract like terms, especially ones with variables like 5x minus 7x, all you're doing is imagine the x isn't there. What if it's just 5 minus 7? You would get negative 2 and then just attach an x to it. So it's not like the x's disappear when you subtract. It's still there. It's just you're just adding what they call the coefficients or subtracting the coefficients. Coefficient of a variable is the number on the left, just sitting out in front of it. And then the other two, it's a little more obvious. Negative 3 plus 8, or subtracting 3 plus 8 will give you positive 5. So there's our answer, negative 2x plus 5. And then also, like the property we had, the commutative property of addition, if you were to switch those two terms, the 5 and then the minus 2x, that's fine. But eventually in this class, we're going to want to get to a point where variables go first, and then, terms that don't have a variable, just regular numbers, go second. So this is correct, but I think you're going to want to get used to just writing them in that order, the variable first, and then the term with no variable attached to it. Yeah, so just know that it's not wrong to put that second thing, but it's not preferred. We'd rather see the other way. Just for, yeah, and we'll kind of see why in the future. It makes things a lot easier to just get used to that. So now this we'll see, I think it's, let's see, where are we seeing it? In chapter 4. So it'll be a little while, it'll be, a month, maybe a month and a half before we get there, but we'll definitely see this in chapter 4. Maybe when we get there, I'll remind you, I'll say, hey, it's been a long time since we did the review video and the review homework. So let's, if you want, you can go back and review it. There are a lot of rules of exponents, and this is going to help a lot in logarithms, which you might have seen at this point, or maybe not. I think when I took this class as a student, the professor said, oh yeah, logarithms, this is review. And I said, yeah, of course it is. And it was not review for me. I had never seen that stuff before. So yeah, but anyway, this seems like silly stuff. Why do I need to know this? But it's useful later in chapter 4, maybe before that a little bit, but mostly that's where you'll see it. So we have this rule of exponents. If you have, they call the b a base to a power, and you multiply it by that base to another power, you can combine them into one exponential expression by adding the powers. So like if you had x to the 5th multiplied by x to the 8th or something like that, I don't know. What you would do if you wanted to combine those into 1x, it would be add the powers. 5 plus 8 is 13. Is that right? Yeah, 13. So that seems kind of silly. Like, what the heck? Why would I ever use that? But yeah, eventually we will use it again. It'll be nice to remember that. Okay, what else? Okay, and then here's kind of a more complicated, obviously, problem to simplify. This is the simple one, but this one, I think if we go slowly and take a lot of slow steps on this one, it'll be okay. Let's see. Okay. What do I got here? I'm gonna go. It looks like it's kind of one term, 4 multiplied by 3x, or x to the 3rd multiplied by y to the 4th, and then a separate one, 10 times. But this is really, the parentheses are not really there for any real reason. There's not really anything I can do. It's not like order of operations. I can't really do anything inside the parentheses because I don't know what x or y are. So I don't really need, I can kind of think of these as all multiplying together. The 4, the x to the 3rd, the y to the 4th, the 10, the x to the 2nd power, the y to the 6th. And then based on the commutative property of multiplication, I can reorder these because I know how to multiply 4 by 10. I don't know how to multiply 4 by x to the 3rd because I don't know what x to the 3rd is. So I'm just going to reorder these so that the ones that I know how to multiply are next to each other. These two, the x to the 3rd and the x to the 2nd power, I can bring those guys together because based on that, the property or the exponent rule we just saw on the previous page, I know how those guys go. And then the y's, those are the only ones I haven't talked about yet. Y to the 4th and y to the 6th. I think I've covered everybody. Oh, why'd I put it 2? I don't know. I do that sometimes, just change a number just for fun, to make life more interesting. Now I know how to multiply each of those. So for example, 4 multiplied by 10, okay, that's 40. And then x, here I'm adding the powers. You can do it in your head, but I'm just going to write it out because this is the first one we're doing. I want to be really careful. And here, same thing, y, add the powers, 4 plus 6. All right, now I think I'm ready to finish it off. 40, x to the 3 plus 2 is 5, y to the power of 4 plus 6 is 10. So that's as good as it gets right there, but it's kind of like you took two of these expressions, 4xy with powers, 10xy with powers, and multiplied them to get just one little expression with a number x and y with new powers. Yeah, so and a lot of these steps you can skip. If you've seen this before, you're probably wondering, why did you show so many steps? A lot of people, I think, that have seen this before, they can just go straight to the answer. They just kind of identify what are like, not really like terms, but like parts to this, the 4 and the 10, and you go, oh, okay, 4 times 10, boom, it's 40. And then x to the 3rd, x to the 2nd, if I add those powers, 3 plus 2 is 5, boom, here's my x. you know, if you feel comfortable, you can always skip all the way to the answer. But, you know, in case this is new or you haven't seen this in a very long time, it's kind of good to know how and why these things work before you try to skip a lot of steps, I guess. Yeah, but eventually it'll be silly to show all these steps. We kind of know how this works, so we can skip it and yeah, move on to just going fast because we have probably other things to do while we're doing this anyway. Yeah. So what else? Let's see. That was fun. Oh yeah, I don't know why it's showing me. We already did that. Okay. Now here's another exponent rule. This one probably won't see as often, but we'll definitely see it when we get to chapter 4, like I mentioned. If you have, instead of something to a power multiplied by something to a power with the same base, what if you're dividing them? Like, if it's, yeah, usually x or a variable is what you're thinking about. X to the 7th divided by x to the 3rd. Like you're thinking, you know, is there a way I could just write that as x to 1 power? Can I simplify that division? Well, they're saying you subtract the powers. So in this case, I do 7 subtract 3. X to the 7 minus 3 is x to the 4th. So that's really all you have to do. If you see something to a power over or divided by something to a power, as long as the bases are the same, you know, if I had an x to the 7th over y to the 3rd, I can't simplify that because they're not the same base. But if they happen to have the same base, like in this first example, yeah, then I can simplify that. So let's see. Okay, that sounds good. What about? All right, so this is kind of, it looks complicated, but we're going to kind of break it down. And yeah, if you've already seen this before, it's probably no big deal to you. But what we can do is we can kind of separate these things. I'm going to write this as 27 over 3 or divided by 3. You can always think of a fraction as division. When you see 27 over 3, that's the same as 27 divided by 3. And then that's kind of multiplied by the x's. I'm going to put those one over the other. This x to the 14th power over x to the 3rd. And then the last guy, y to the 8th over y to the 5th. And I kind of separate them. You don't have to write it like this, especially if you feel comfortable, but it's kind of showing why the rules we had apply and how we're able to do the things we do. Here I'm just dividing. I got 27 divided by 3, that's 9. X to the 14th divided by x to the 3rd. I'm going to just write it out, but feel free to skip this step and do it in your head. I'm subtracting the powers because we just saw that was the rule in the previous page. Yeah, if you want, you can just subtract it in your head, but I just want to show it. Same thing for y, power of 8, subtract 5. Okay, that's equal to, the 9's not changing, just these guys. 14 subtract 3 is 11, so that'll be my final power on x. 8 subtract 3 is, or sorry, I gave the answer away in the question. 8 subtract 5 is 3, and that's as good as it gets. They got a number, an x, and a y. There's not really any way to simplify that. They're totally different things. I don't know what x is, I don't know what y is, so yeah, these things, there's no way to really, you're just making something terrible look less terrible. It's like this thing was complicated and there were a lot of ways to simplify it, and we did that. But definitely if you feel comfortable, just go ahead and skip to this. You could have just said 27 divided by 3 is 9. If I subtract the powers on x, I get 11. If I subtract the powers on y, I get, 3. You don't have to write all that out, but yeah, like I said, I think if you're not familiar with this stuff, if you've never seen it before, it's good to go slow at first, especially to prove to yourself you can actually do that. Okay, and this is the weirdest rule. This is the one, it's easy to forget because you don't see it very often, and it doesn't even make any sense. If b is any real number other than 0, if you raise something to the 0 power, you get 1. That one just, it's kind of mind-blowing, but something, any number, let's just say 3. 3 to the 0 power is 1. That one, if you kind of try to reason it out, like, oh, if you had a power other than 0, what if it was 2? That means you multiply 3 by itself 2 times. You know what I mean? That logically makes sense, but how the heck do you raise something to the 0 power? That means 3 multiplied by itself 0 times. What? Doesn't even make sense, but someone just made up this rule because it kind of fits in with all our other exponent rules. This doesn't make any sense in and of itself, but if we didn't if this rule wasn't true, all our other exponent rules wouldn't make sense. And then, for example, this is one way, or one reason why, the rule we just talked about was if you have something to a power, I don't know, x to the 9th over the same base, but to a different power, you subtract their powers, right? That was the previous rule. So 9 minus 4. So if you think of it that way, what if I had the same power on the top and on the bottom? Well, I know in one sense that those will cancel each other, That's a fraction where the numerator and the denominator are exactly the same. So that's going to be 1. That's like if you had 3 over 3, you know, the same thing over the same thing. 3 divided by 3 is 1. X to the 9th divided by x to the 9th is 1. So in one sense, I know that that should be 1. But in the other way, based on that rule we saw on the previous page, I should subtract the powers. X to the 9 minus 9 is x to the 0. So based on just old fraction knowledge I have, I know that this expression here should be 1, but based on our new exponent rule from the previous page, it should be the same as x to the 0. So we just kind of declared that that's true. Anything to the 0 power is 1. If that's not true, then our other exponent rules don't make any sense, and yeah. So it's kind of like, I think someone just made it up. They said, oh yeah, these are all our exponent rules, and then they found this and they said, oh, uh-oh, does that mean I did something wrong? And let's just say that anything to the 0 power is 1. Then I cover myself and I'm not wrong. All my other declarations of exponent rules are right. Yeah. So don't try to logic it out. It doesn't make sense. It's just memorize it and move on. I'll try to remind you as time goes on too. Here's yet another exponent rule. And this one too doesn't make any sense. Anything to a negative power means you're making it a fraction. So if it was 2 to the negative 3 power, that logically that doesn't make sense, kind of like 0 power. I can't raise something to a negative 3 power, right? That doesn't make any sense. Because I would say 2 multiplied by itself, negative 3 times, like that doesn't even make any sense. This is just a rule we have to memorize, and logically it doesn't make sense. But it fits in with all our other exponent rules. It just means make it a fraction, make it 1 over that thing, but now the power is positive. The negative power was just there to tell you, make this a fraction. Once you make it a fraction, no need for the negative anymore. And then you can simplify that, 2 to the 3rd power, that's 2 times 2 times 2, 3 of them. 2 times 2 times 2 is 8. So really it's weird, but 2 to the negative 3rd power is 1/8. And that's probably, honestly, that's something I would forget. Here I see it. If I was a student, by the time I need it in chapter 4, I'm probably going to forget it. But that's normal. If you don't use something that you learned, you're not going to remember it, but that's normal. All right, so here's another example. Let's try this guy here. We've got 5 to the negative 2. That logically, this doesn't make any sense, but that means 1 over 5 to the 2nd power. And then, like I said, no more negative, because the negative was just there to tell me to put it under a 1 as a fraction. And then I'll simplify that. 5 to the 2nd power means 5 times 5, so 25. There we go. Looks good. Okay. Yeah. It doesn't make any sense. When you look at this and your answer, it's like, what? How can those be the same? You know what? There's certain rules in math that they don't make sense, but we just kind of go with it, I guess. It's kind of sad. Okay, now let's try this other one here. So this is almost like, it doesn't look like it, but I can think of this as 3 multiplied by x to the negative 6 multiplied by y to the 4th. And I think I used to tell my students that when we used to offer just an algebra class at this school, and we'd had a lot of time to go over this stuff, I would say, if you have an expression like this, only the parts of it that have a negative power need to move to the bottom of the fraction. This 3 doesn't even have a power, so he can stay right where he is. The y doesn't have a negative power. He has a positive power, so he can stay there. Oh, well, maybe I shouldn't do it like that. Let's see. Just at first, because this is really weird stuff. I don't want to make it too weird. Okay. So the x, though, he does have a negative power. I'm going to put him as 1 over x to the 6th. And then y to the 4th, he's not going to go down in the fraction because he doesn't have a negative power. And then if I want to kind of try to combine this all into 1, again, I only separated it just so I can kind of remember that only the x has to go down to the denominator. If I want to multiply across, I can put the 3 over 1 and the y over 1. And the numerator now is just 3 multiplied by 1, which is 3 multiplied by y to the 4th. So on the top, it's just like the x disappeared. And in the denominator, I have 1 times x times 1, or I should say 1 times x to the 6th times 1, which is x to the 6th. So really what happened was nothing really changed except the x, he had to move downstairs. I always think of it as, if you have kids, if one's doing something bad and the other one or the rest of your kids are being good, you're not going to punish all of them. Well, usually not. You just say, hey, the one doing something bad, you go in timeout. Everybody else can just stay where they are. Kind of like that x to the 6 is negative. He's doing the bad things, or she's doing the bad things. Yeah, well, I know I'm biased because I have one girl and one boy. Usually the girl's doing good things and the boy's doing the bad things. So when I said he's doing the bad things, I was thinking of my son. because he's usually the troublemaker. But yeah, not always true. All right, another, oh my God, another exponent rule, Lord have mercy. So this one, I think to me, at this point, if I were, not familiar with exponent rules, this would remind me a lot of the other one, because the other one we had was b to the m, I think this is how they wrote it, multiplied by b to the n. You add the powers, m plus n. But that's if you have the same base, b times b. This is just one base with two powers. So it's like, it looks a little different. B to the m, that part looks the same, but it's not multiplied by b to the n. It's just that to another power. In this case, you multiply the powers. So it's very subtle, the difference that here you add the powers when you have two separate bases, a b times a b. But when you just have one base with two powers, you multiply their exponents or powers. So very, very subtle difference, but it's important. So if you had 2 to the third and then to the fourth power or something like that, I would multiply those powers. 3 times 4 is 12. But versus if it was the old exponent rule, it would look more like 2 to the third multiplied by 2 to the fourth. Then I would add 3 plus 4 is 7. So those are different problems, but they look very similar. You got to be, I guess, really careful. There's very subtle differences, but they're important. Oh, math. As I teach math, I always want to say, apologize. I'm sorry. There's just so much to remember. And so how about this guy? 3 to the third power to the second power. Try to simplify that. First, I would say, well, there's only one base. It's not like it's 3 to the third multiplied by 3 to the second. So it's going to be the multiplication type of thing. 3 times 2. Feel free to skip that step and just multiply in your head. 3 times 2 is 6. There we go. And then sometimes they're okay with you leaving it like that. But I guess if that power was smaller, you might actually multiply 3 by itself. But 3 multiplied by itself 6 times is pretty serious. I can't do that in my head, Yeah. I mean, that's what it means. But I think that's almost such a big number, you could probably just leave it like 3 to the 6th power. Yeah. Or use a calculator. Don't be a hero. That's what I tell my students sometimes. You don't need to do all the math in your head. Like I'd say the stuff we've been doing so far, you could probably do this in your head. The calculator probably won't help you with a lot of it, but just multiplying big numbers, you don't need to be a hero. Just use a calculator if you want. Yeah. Unless you're just trying to exercise your brain, that's cool. Okay, let's see. Now, the second one, we haven't done that yet. This one's kind of weird. It really helps me to write it out. B to the, and this is, again, it's just one base and two powers, so I'm multiplying the powers. It's a similar situation to the first one, except it looks weird because the negative powers. But still, I'm multiplying. So -3 times -4 is +12. There we go. That's it. Yeah. So the negative powers ended up becoming positive, which is kind of nice because they looked scary at first. All right. Yeah, that looks good. Nope. Let me get rid of all this writing here. Okay. Okay. So this is the rule. Well, the product rule for exponents. This is now it's the previous page. We had something to a power. Oh, it was like m and n. That's if you have one base with two powers. This is kind of the opposite. What if you have two bases multiplied together and a times a b with one power? You can distribute that power. That's fine. So, but that's only if multiplication is the operation inside. So I might even make a note here. If you don't have to, if you don't want to, we can distribute an exponent across multiplication because a times is being multiplied by b. Even though you don't see the operation, they're still multiplying. Multiplication, but not addition or subtraction, because I think I forget that sometimes, and I know students kind of mix it up. So this rule says it's okay to go like if you had x, y, or x times y to the power of 5. If you want to get rid of the parentheses, you can just kind of give each of them their own power of 5. X gets a 5 power, y gets a 5 power. That's true, that's good. But if it was x plus y or x minus y to the 5th, that is not equal to x to the 5th plus y to the 5th. So that operation between the x and the y has to be multiplication in order to distribute the power. This we'd have to do a different way, which we'll talk about later. Yeah, I just want to make sure that's clear because it's not obvious. Yeah. This almost feels like this rule says you can always distribute a power. That's fine, but it's only across multiplication. Let's see. Okay, what else? Okay, now they're saying, okay, here's an example. Let's try to simplify it. And this one's kind of nice because it has some a variable, but it also has a number. So okay, this is, and that's it is multiplication inside. It's -4 multiplied by x. So I'm safe to multiply or to distribute the power. -4 to the third power times x to the third power. And then I think this is, I can't do much with that because I don't know what x is. He's going to just stay the same, but -4 to the third, you can either do that in your head or write it out. -4 times -4 times -4, there are 3 of them. And then like with one of those properties we had, was it the associative property of multiplication? You can just do 2 at a time. -4 times -4 is +16, but I still have to multiply that by that last -4. And feel free to skip a lot of the steps. You can do it in your head. Now I can multiply 16 times -4, I think is -64. Is that right? And then just keep the x to the third. Yeah, okay. That looks good. Yeah, I think, especially on a test, if you're taking a test, I would say show as many steps as you can, just because skipping steps, I know I make mistakes in my head if I skip a lot of steps. For homework, it's probably okay because you enter your answer in the homework and it tells you, yeah, you're right, or no, you're wrong. So it's not too big a deal and you can try it again, but with tests, you can't try it again. This is it, you know? So yeah, I would probably try to show some work if I'm doing a test or yeah, something like that. All right, so the quotient rule, when a quotient is raised to a power, raise the numerator to that power and divide by the denominator to that power. I think what they're trying to say is that distributing the power, it worked on multiplication and it also works on division. So remember we said you can't do it with you can't do it with addition, but you can do it with multiplication. So you can, yeah, I should say you can distribute exponents across. On the previous page, we figured out it was multiplication is okay. Multiplication. But now we know it's or division. Or division, but not addition or subtraction. I cannot addition or subtraction. So like we mentioned, I think I did x plus y to the fifth. That is not x to the fifth plus y to the fifth. That's way more complicated. This is something actually we'll see in chapter 8. Yeah, or subtraction as well. It's a lot more complicated. We'll see it later. That's not x to the fifth minus y to the fifth. This is only true. Yeah, the distributing thing is only true for multiplication or division, not if the operation is addition or subtraction. But here, you know, you have a divided by b or a over b. If you think of it as a fraction to a power, you can give the numerator that power and you can give the denominator that power. So just because I think we said if you simplify something, there should be no parentheses. That's how you know you've simplified it, or part of the way you know you simplified it. All right, what else? Here we go. So here's an example. We can do negative, and then we got 2 to the fifth. In this case, the negative is there. Yeah, that's okay. And then y to the fifth. Give each of them their own power of 5. 2 to the fifth. Okay, that's 2 times 2 times 2 times 2. There's 5 of them. Y to the fifth, I could do that too, but why do that? Because I don't know what y is. I can't simplify it. 2 multiplied by itself 5 times, I think it's 32. There we go. Y to the fifth. Okay. But yeah, I think what did we see earlier? It was like 3 to the 6th power. That one was a little large. I think 2 to a power, usually it doesn't get too big, but at a certain point, it gets so big that they might let you leave it as something to a power. But if it was an exam, I'd probably specify, like, you know, multiply it out or something like that. So you know, when would I multiply this? When would I not? Okay, let's try this next one now. So he gets the power, x to the fifth. Now I'm going to be careful here. I recognize that I probably need to use another exponent rule here. I already had x to the fifth, but now he's getting this other power 3. And the 3 in the denominator is going to get this power of 3. So let's see. I'm going to go, I've got to remember x to the fifth to the third. Do I add those powers or multiply? If it was x to the fifth times x to the third, I would add, but in this case, I'm multiplying. Multiply powers. 3 multiplied by 5. And then here, this is probably small enough. That's 3 times 3 times 3. 3 of them. That's not too big. I can multiply that out. That's 27. There, that looks good. Okay. Oh, let me get rid of this stuff. Clear. All right. simplifying exponential expressions. An exponential expression is simplified when, this is kind of the question. If someone says simplify and you do one thing to simplify it, but then you say, well, is it done? I mean, I simplified one part of it, but is there more to do, or am I done? That's kind of a tough one, but this tells you when you know. If there are no parentheses, we kind of talked about that on the previous page because we saw, what was it? It was, I don't know, x over 3 to a power. You know, that means it's not simplified. I could probably have to distribute the power and blah, blah, blah. I don't want to see parentheses in my answer if I can help it. No powers are raised to powers. So yeah, if you saw on the previous page, x to the 5th to the 3rd, don't leave your answer like that. You know, multiply the powers like we saw. Each base occurs only once. So if you ever see like a fraction x to the 15th over x to the 6th, you don't want to leave it like that because that's almost like low-hanging fruit. We know a way to simplify that. You know, you subtract the powers. And there should be no negative or zero exponents because we know that if you see something to a negative power, that means 1 over that thing. So if you ever see an exponential thing to a power that's negative, try to rewrite it as a positive by putting a fraction. And then also if you saw something to the 0 power, just replace it with 1. And if you do all those things, you should be probably good for exponential stuff anyway. Okay. Let's see what else we got. So we'll simplify this guy. Yeah, this looks good. This one I can probably skip a few steps because I kind of know. I'm multiplying the exponents. The variables that have existing exponents, I'm going to multiply them by that 4 outside. The 2 is going to get the 4th power. The x to the 3rd is going to get the 4th power. And the y to the 6th is going to get the 4th power. This I can just multiply out. 4 times 4 times 4 times 4. 4 2's make 16. And then I'm going to multiply the powers of x to get 12. Multiply the powers of y to get 24. There we go. That looks good. And then the more of these you do, the easier it gets too. And similar for this guy. Ooh, this is tricky. This is actually a good, they kind of left this to chance, but I'm going to say, if you have we didn't say this, but if you have a fraction to a negative power, there's a rule. I think you can get this rule out of one of the other rules, but whatever. Something to a negative power, it means flip the fraction upside down. So numerator becomes denominator, denominator becomes numerator, and now it's a positive power. Because we knew what to do with, you know, a whole number to a negative power, you flip it upside, or you make it 1 over. But if it's already a fraction like this one, I'm going to flip it upside down, y to the 4th over 5x. I flipped it totally upside down. Now that second power that was negative can become positive, and now I can proceed the normal way. I know everything's either multiplying or dividing here. I'm going to give that y to the 4th power his own second power. And then this is kind of taking it really slow. 5x is the denominator. He's going to get a second power. So I just distributed the power between the division or the fraction. In the numerator now, I know I'm multiplying those powers. 4 times 2 is 8. And then the denominator 5. Now I know that inside the parentheses, there's a 5 multiplied by an x. They both need to get that second power. 5 to the second power, x to the second power. And I'm pretty much done. I think y to the 8th, I can't do much with that. X to the 2nd, can't do anything with that. But the 5 to the 2nd power, I can say 5 times 5 is 25. That's not too big of a number. So I think you'd probably be expected to simplify that guy. Yeah, now it's getting complicated, huh? Oh, can't see because all the writing. Okay. In general, if b squared equals a, okay, this is talking about square roots. So this, I mean, I think sometimes the way things are written, it's not obvious what they're trying to say. But let's just say, for example, well, maybe we'll just read it for a second. In general, if b squared equals a, then b is the square root of a. It's like, what? Okay. This is the definition of what they call the principal square root. If a number a is a non-negative real number, we don't want to talk about negative numbers in a root. The non-negative number b such that b squared equals a, denoted by b equals the square root of a, is the principal square root of a. Oh my gosh, that's like, just reading that might put you to sleep. If you have insomnia, you read that and you just go right to sleep. No. What they're saying is, if you see an example like square root of 25, that's asking what number, and this might be easy for you. You can always skip ahead if you've seen this before. Multiplied by itself is that number there, 25. So do you know a number that you multiply it by itself and you get 25? Well, 1 times itself is 1. That's not it. 2 times itself is 4. 3 multiplied by 3 is 9. 4 multiplied by 4 is 16. But 5 multiplied by 5 is 25. So that's the answer. And I think what they're trying to say here is, yeah, like the square root of 25 is 5 because 5 to the second power is 25. That's what this kind of notation is here. They're trying to explain it, but because there's no numbers, it's kind of, I don't know. They're doing their best, but it's confusing. Yeah, so that's what you do when you see a square root, that symbol right there, that just means what number multiplied by itself is this number inside, and then that's it. Okay, so here we go. So square root of 81, that's you saying what number multiplied by itself is 81. And you multiply numbers by itself enough to know that 9 times 9 is 81. Because 9 to the second power is 81. Or 9 times 9 is 81. Yeah, okay, how about? And this one, they're trying to confuse me. If there's a negative in front of the root, just kind of keep it along with you. The answer is going to be negative, and then say, okay, what number multiplied by itself is 9? That's 3, because 3 times 3. Because 3 to the second power is 9. It just happens that the negative's in the front. He's just along for the ride. He's just there to see what happens. And then this part, this part, they're trying to trick us. This is, I don't want anybody to think this is true. That's not the same as, I can't split it into 2 roots like that. Like, I mean, I do know there is a square root of 36, because 6 times 6 is 36. I know there's a square root of 64 because 8 times 8 is 64, but you can't split the square root. You have to just simplify what's inside first. 36 plus 64. It's almost like order of operations. Think of the square root as parentheses. I have to do what's inside the parentheses of the root first. Add the numbers. 36 and 64 is 100. And now I can take the square root of that. 100 is, the square root of 100 is 10. Not that you have to write this, but in case this is kind of new or it's been a long time, because 10 to the second power is 100. Yeah. So that one, they try to trick me on that one. If you did it this way, it wouldn't be true, right? The square root of 36 is 6. The square root of 64 is 8. 6 plus 8 is 14. That's not the same as 10. So this is definitely not the right way to do it. They wanted me to be tricked on that one, and it worked. I was tricked. Okay. Yeah. I think that page is just saying all the same crap. So that, that last example we saw, it was the square root of 36 plus 64. I cannot split a root across addition when it's adding like that. But if they were multiplying, I could. That's what this rule says. So if I had, I don't know, the square root of 9 multiplied by 16 or something, I could multiply those numbers, 9 times 16. That's going to be a big number, and bigger numbers, I don't really know their square roots as well as I do little numbers. So I might want to split that. Square root of 9 times the square root of 16. And like I said, I'm only able to do that because this rule says I can do that when it's multiplication inside, not addition. This is no good. And then that's good because I know the square root of 9, that's 3, since 3 times 3 is 9. And 16 square root is 4, because 4 times 4 is 16. And now I can just multiply those. 3 times 4 is 12. Oh my gosh, that took me a second. Yeah. But then the other way as well is important. So, yeah, anyway, yeah. We'll see that. Okay, now this is, I think the presentation here is almost makes this seem simple, but it's not simple. Now we're talking about simplifying square roots. That's where if the number inside doesn't have a square root, I'm going to write that down because this is not easy. Maybe if you've seen it before, you think it's easy, but if the number in the root has no square root, like in this example, 75, I don't think there's any whole number that's square root of 75, because here's my list. 1 to the second power is 1. That's not right. 2 to the second power is 4. 3 to the second power is 9. 4 to the second power is 16. 5 to the second power is 25. 6 to the second power is 36. I'm not going to go too high. 7 to the second power is 49. Oops. 8 to the second power is 64. 9 to the second power is 81. Maybe 10, I'll stop there. 10 to the second power is 100. I think if 75 had a square root, we would have seen it somewhere in here. These are all the whole numbers, square roots. And then, yeah. It should 75, if he had a square root, he'd be somewhere between 8 squared and 9 squared, because 64 is 8 squared and 81 is 9 squared. So this guy doesn't have a square root outright, not a whole number anyway. So if that's true, then we do what we can and try to simplify it. Simplify by thinking of the largest number that divides into, in this case, 75, that has a square root. So I look at 75 and say, okay, what divides into 75? Let's see. 81 has a square root. Obviously, I built it to have a square root. It's 9 squared. That doesn't divide into 75. Neither does 100. They're too big. Can 64 go into 75? No. 49? No. 36 doesn't divide into 75. 25 does. Yeah. So 75, this is in my thinking, I'm thinking, oh, 75 is 25 times 3. So I think 25 is the biggest number that divides into 75 that has a square root. And I think it's really helpful to have this. If you're really not familiar with this stuff and you don't feel comfortable, it's kind of nice to have this little cheat sheet on the side where I have all these numbers. These are the only numbers that have square roots because they're all the whole numbers to the second power. And then, so with that in mind, I should be able to split this based on that rule on the previous page. I'm going to rewrite 75 as 25 multiplied by 3. And then based on the rule on the previous page, I can give each of them their own root. It's kind of like there's no hope of simplifying this whole thing down to a whole number, but at least part of it. With 25, he has hope of being simplified. 25 square root is 5. There is no square root of 3, so I'll just leave it that way. So it's almost like, yeah, 75 doesn't have a square root, but a piece of it does. So I'd like to extract that piece that does and leave what's left. Kind of, yeah, kind of complicated. That one, I was looking at, there was another example, but I'm going to do it over here. Actually, that example, I'm gonna do another one. So sorry, I'm not gonna look at this yet. I'm gonna try to do a new example. Simplify. What's a good one? Square root of 32. How about? Dang it, I shouldn't have erased that list of numbers that have square roots, but 32 does not have a square root. But I'm looking at, the numbers that do have square roots are 1, 4, 9. In my head, I'm just squaring everything. 2 squared, 3 squared, 4 squared, 5 squared. 6 squared. Okay, I think I can stop there because I'm getting to a number that's bigger than my given number. What's the biggest one of these that divides in? So what you want to do is, for example, 4 divides into 32, but it's not the biggest one. So you want to grab the biggest one. 36, or sorry, 36. 16 divides into 32. That's what I want. The 4 would work, but there'd be more work to be done. I'd have to simplify again if I did 32 is 4 times blah. That's what I want to do. 32 is 16 times 2. I can give each of those their own square root. Like in the last one, in the hope of 16 has a square root of 4. 2 doesn't have a square root, but at least I got something out of it. That's the idea, sort of. Yeah, I think that looks good. So we'll see it more in the next section of the book. So we'll get a lot more practice with it. It's really not easy, but it's good to at least have seen it. It'll become easier as we go. Another one similar to the product, if you have two things multiplying in a root, you can split it into 2 roots. Same thing with division. If you see a divided by b in square root, you can give the numerator and denominator their own roots, and yeah, and then it's all good. That's only for multiplying or dividing inside of a root, but if you have any addition or subtraction, it doesn't work. Kind of like with powers, huh? Okay, so here's an example of trying to use it. This right here is difficult. What's the square root of 25 over 16? It's like, what number multiplied by itself is 25/16? That's tricky, but if I split it between the numerator and denominator, now it becomes 2 simpler problems. What's the square root of 25? Okay, is there a number multiplied by itself that makes 25? Yes. 16? Yes. 4 times 4 is 16. So it's that, I guess what they're just trying to say is that if you have a fraction and a root, you can just think of their square roots separately. What's the square root of the numerator? Write that down. What's the square root of the denominator? Write that down. And then this guy, similar, when I'm looking at this, I guess this is us using the rule backwards. If you want, like in this one, you can start with the fraction inside the root and split it if it helps you, like we did. But in this case, I think they're 2 separate roots in part B here, and I can bring them together in 1 root. Because I'm looking at the 150 and the 2, those together can divide to make something smaller, you know what I mean? And then the x over x. So sometimes sometimes it can benefit you to take a fraction inside a root and split it into 2 roots, but other times you're given 2 roots and it's kind of beneficial to combine them into 1. So let's see, in this case, yeah, they say, all right, instead of writing a root over a root, I'm just going to put it all under 1 root. and then simplify. So I can kind of like we saw previously without, I think we've seen this in a previous slide without the root. It was just a number over a number. I can simplify that. 150 over 2. I can divide 2 into 150. And then subtract the powers. So this one's a little tricky because it's x to the third over x. Think of the x as a 1 power. And I subtract them. X to the 3 minus 1 is 2. That's why we get that. And then that 75, I can simplify more. I think we saw that guy before, right? It was square root of 75 on a previous page was 5 square root of 3. I think we simplified that on the previous page. Yeah. And then the x part, that's kind of tricky. Let me see. This part here, you got the square root of x squared. That's confusing, but that's saying what can be multiplied by itself twice to give you x squared? Well, x. So that's kind of tricky, actually, and we probably won't see that too much. I think that's probably okay. Adding and subtracting roots. Okay, this you won't see too much. You'll see it a little bit in the next section, but after that, you probably won't. This one, think of a root as, if you want to combine like terms, think of a root like a variable. A root like a variable. We can combine like terms if they have the exact same root. So that in this example, the 13 is inside both roots, so that's fine. We can add those. And almost treat it like a variable. Like I said, I almost think of it as 8x plus 9x. 8, you just add the numbers in front like we discussed earlier, 17x. So same thing here. I want to add the numbers that are inside the root, but I'm not supposed to. I just leave the root the same, which is kind of weird. But yeah, and if the numbers inside the root were different, we couldn't add them. And then this one, similarly, okay, I'm checking. There's a root. This guy has a root. Are they the exact same root? Yes. The coefficients are different. This guy has an invisible 1 in the front. This guy has a negative 20. But the 17 and the x are all inside the root. So almost think of this as like a variable 1z minus 20z. Just subtract their coefficients. 1 minus 20 is negative 19z, I guess. Yeah, in this case, I'm going to do negative 19 square root of 17x, I guess. That's weird. That's weird. You won't see that too often, but yeah, you treat it like a variable. Don't add or subtract what's in the front. All right, now we're getting into what if you have not just a square root, like here's square root of 16, I don't know, versus what if you have a little number there? What's the difference between that? That's called the index, that little number, and this here they write it as n because it could be something else. This, like for example, this is saying what number to the second power is 16, and the answer is 4 because 4 times 4. This, if you see a number in here other than 2, that's saying what number multiplied by itself that many times, or what number to that power is 16. Number to the third power is 16. That's a little trickier. Yeah, that one's not obvious. That one actually, there is no, they call it a cubed root. There is no cubed root of 16 because I don't think there's any whole number that you can multiply by itself 3 times to get 16. There is a fourth root of 16 though. 2, because 2 to the second, or sorry, 2 to the fourth power is 16. That's tricky. So it's like, once I understand the roots, then all of a sudden, yeah, okay, don't worry about that. All right, so this is saying 3 to what power is 4, or sorry, what number to the third power is 40? You know what? I think these are too complicated for now. Maybe we'll come back to those later. Let me just think about like third root of, you know what? No, I don't want to, this is too complicated for now. I think we'll get into this later if it's even important. Yeah. That's not that important. Yeah, maybe, yeah, I want to just give you what's important. I don't want to confuse everything. This you'll see in chapter 4 again. This is like, anything to the 1 over n power means the root. So remember that other rule we had? It was like anything to a negative power really means 1 over that thing. And we said it doesn't really make any sense, but this is something you memorize. If you have a fractional power 1 over something, that means that kind of root. So you'll, for example, if you just had 2 to the, no, not 2, about 25 to the 1/2 power, that means 25 is in a root and the index is this number in the denominator 2. So it's really 25 to the 1/2 power really means the square root of 25, which is 5. And what else? Let's say you have 8 to the 1/3 power. That means 8 is in a root and the index is 3 now because the denominator is 3.